Hello all, hope you're doing well. So in this video we are going to discuss about organic chemistry basics, and we can't define organic if it is not about carbon. So carbon is atomic number 6. It has electronic configuration of 2 and 4. So I'm still not discussing from the SPD hybridization, SPDF, not hybridization, electronic configuration. So that we'll discuss later on. For first, when I've finished that atomic structure part. So if we see carbon is having four valence electrons, so definitely it can form four covalent bonds. Now carbon can do multiple bonds also, because in covalent bonding we have double triple bond also. We don't have any atom having four bonds, like it cannot form four bonds like this is not possible, because in this case the atoms are going to come so close to each other that repulsive forces will dominate and there will be no attractive forces at all. So before starting about carbon, so let's discuss about occurrence of carbon. So carbon can be present in free state, it can be present in combined state. So free state is in the form of allotropic form, that is diamond, graphite. These are allotropes. Allotropes are the pure forms of carbon having similar chemical properties but different physical properties. So the structurally they are different, chemically they are just made up of carbon, elemental form of carbon only. And then we even have coal. So these are free states of carbon. And if we say coal, it's an impure form of carbon. So it varies from 60% to 90% of carbon in it. Rest are impurities, rest maybe some other elements also might be present, but diamond and graphite are pure forms. So this is a free state. Then we come to the combined state. So in combined state, we have solid state, liquid, and then we have gaseous state. So under solid state, we have a lot of compounds like magnesium carbonate is there, that's a salt. It's limestone, we even call it as marble or chalk. Then we even have sorry, this is calcium carbonate. MgCO3 is magnesite, that is magnesium carbonate. So this is again a different kind of salt. Calcium carbonate is chalk, this is limestone, marble. So these are the common names of this compound. Then we even have specifically, if you see in solid state, we will be saying a lot of carbonates. So in the form of carbonates we will see a lot of mineral salts, right? So that is the only possibility for carbon to exist. In the form of carbonates, mineral salts, we have carbohydrates also, we have fats also, cellulose is also there. So fats, protein, we are also made up of carbon. So then we can even add zinc carbonate. Zinc carbonate is also called as calamine, that's a common name. It's an ore of zinc in the form of carbonate. Even magnesite is a ore of magnesium. Same applies for limestone, marble, or chalk. Then, if we come to liquid state is we have a lot of oils are there, like petroleum is there, diesel is there. Then it's a mixture of different kind of carbon compounds. So kerosene is there, wax, grease, so many are there. These are all in the liquid state. Even vegetable oils that we eat at home, that we consume at home, they are made up of carbon only. So they are hydrocarbons, compounds of carbon and hydrogen. Then in the gaseous state, we have carbon dioxide. It's present in the atmosphere, that is 0.03 percentage. Then in the gaseous state, we can even say natural gas is there. Natural gas is majorly methane in it, CH4, that is also carbon based compound. It's a hydrocarbon. So natural gas or compressed natural gas, we can say. So the major component is methane in it. Then petroleum gas is there, coal gas is there. So many compounds are there in the gaseous state. Then after this, carbon covalent bonding we have already discussed. So I'm not going to touch that part. You can see my other videos of covalent bond and you can understand. But yes, wherever bonding is required, that we'll be discussing for hydrocarbons, not for in single, double, and triple covalent bond, the electron dot structures that I'm not going to discuss. I think for most of the molecules I've discussed already, water have discussed, ammonia have discussed, carbon dioxide we can discuss. So just some examples of covalent compounds we can discuss the structures. So carbon dioxide, in this the central atom is carbon. So carbon again is having four valence electrons. So you can show four dots or four crosses, leaves structures over here. So oxygen is atomic number 8, 2 and 6 configuration. So 6 valence electrons we have to show. So make sure that you show two electrons in front of this carbon so that you can show the overlap. Now you can show the overlap like this. Oxygen is sharing two electrons. You can show the overlap like this also. And carbon is going to share these two electrons each from this oxygen. So you can see the octet is getting completed. We'll be discussing about drawbacks of octet theory also later in this, not in this video, in the separate video. So if you see over here, oxygen is already having 6 valence electron, 2 electrons it's going to share, so octet of this oxygen is done. Similarly for this oxygen is also done if you count 8 valence electrons, and this carbon is sharing 2 electrons each from this oxygen. So we have double covalent bond and the lone pair of electrons are intact. So there are total 4 lone pair of electrons, and we have four bond pairs. We have no single covalent bond, we have two double covalent bonds, and on each oxygen we have two lone pairs. And it's a linear shape. If you can see, it's 180-degree angle, right? So we are not discussing bond angle, but at least you should know about it. Then we go to this particular molecule that we can discuss, C2H4. This is called as ethene. The naming nomenclature part we'll be discussing about hydrocarbons in a couple of minutes. So C2H4, if you see, it's carbon. So two carbon, definitely they are bonded to each other. And then we have four hydrogen, if you can see. So I'm just placing it over here just to make sense. So carbon over here is having how many? Four valence electrons. So definitely there is a double covalent bond in between two carbon, because carbon needs to form four covalent bonds, right? So we can't just leave the fourth electron anywhere over here. So hydrogen has a shortcoming that it can form only single covalent bond over here. With every hydrogen it's going to be single covalent bond here. So obviously the rest of the electrons are going to be sharing with the carbon itself. Carbon can form multiple bonds with itself, something we call it as catenation, that we'll do in the special properties of carbon. So you can show the overlap, you can show with the electron dot structures, you can show the structure, line structure also like this. So here. Similarly, you can try for C2H2. This is called as ethyne, and carbon over here is having a triple bond. You can make it on your own. You can try it. Then we come to the, so you can stop the video and you can try on your own. Then we come to the next part, that is properties of covalent compounds. So if we talk about physical state, so they are generally gases and liquids. Now when I say generally, that means we can have solids also, right? But solid is like, you can say cane sugar is there, cane sugar is there, glucose is there, urea is there, they are solid, right? But generally it's going to be liquids or gases. And mass plays an important role over here. The higher molecular mass of any organic or any covalent compound, that means they are soft solids. They are not going to be very hard solids, but soft solids, I would say. So iodine is a covalent molecule, I2, that is a high molecular mass. That is also a sublimable solid, and the color of iodine is violet. So if we say for gases, we have these are gases which we discussed: ethyne, ethene. These are hydrocarbons. These are low hydrocarbons. So these are gases. We have carbon disulfide, that is a liquid. We have carbon tetrachloride, that is also a liquid. So we have methane, which is a gas. Even benzene is a liquid. C6H6. So we have gases, we have methane, we have C2H6 ethane, we have C2H4 ethene, C2H2 ethyne. So many examples are there. For solids, I just told you about, we can actually write more over here under the solid category. So solid can be iodine, I wrote already, cane sugar. So sugar in general, we can write the formula C12H22O11. Then we have urea. About urea, we are going to discuss in a couple of minutes. So NH2CONH2, that's our organic compound, it's urea. Glucose, I think everybody knows, C6H12O6, that's a formula. So these are covalent compounds, but they're solids. Then we come to the next property, melting and boiling point. So melting and boiling point is generally going to be low. The values of melting and boiling point are going to be low for this. So they are, you can say, covalent compounds are not electrically, you can say, made up of electrically neutral molecules, right? So you can say the force of attraction between covalent compounds is quite weak. Like, at least the compounds I'm talking about, like if I say chlorine is one molecule and another chlorine, if we say, the interactions between these chlorine molecules are going to be very weak, intermolecular forces that we say. So very small amount of heat energy is required to break these intermolecular forces. So obviously that leads to low melting and low boiling point. And we can take one example of naphthalene balls we have. So naphthalene balls have a low melting point of somewhere around 353 Kelvin. And if we say carbon tetrachloride, that is also having a low boiling point for somewhere around 350 Kelvin. So we do have exceptions like diamond and graphite. These are covalent solids and they have high melting and boiling point. So that exception you can write. Then next property is solubility. So in general, they dissolve readily in organic solvents. Inorganic solvents, not inorganic solvents. So organic solvents that we are talking about is ether. Ether is a type of organic compound. It's you can say the IUPAC and structure, everything we'll discuss later on. And water, it is insoluble. So, but if we say like naphthalene, let's say take talk about this naphthalene again. Naphthalene is very much soluble in ether, but it's not soluble in water. So we can remember like that. Then if we say urea, if we say this urea, glucose, cane sugar, these are very much soluble in water. So you cannot say that most of it, again, depends upon the interactions between them. It depends upon various other factors that we are not discussing, at least in this video. But some of the covalent compounds can dissolve in water, some cannot. Again, it depends upon their interactions, different properties. Then even HCl, if we say hydrochloric acid, that is, you can say, a covalent molecule. Again, it's an inorganic acid, but it is soluble in water. Then we can even, last property is non-conductor of electricity. they cannot conduct electric current. Generally they cannot. Like if you say urea, glucose, cane sugar, carbon tetrachloride, these cannot conduct electric current. But if you talk about HCl, it can conduct electric current in the presence of water. But water in the pure state, it is a poor conductor of electric current. So HCl can release H positive or hydronium ions only in the presence of water. So it can conduct electric current, but only in certain cases, but not all covalent compounds are going to do so. So these are properties of covalent compounds. Next we are going to discuss about is special characteristics of carbon that makes it very much special. So the first one is small size. So since carbon is a 14 group element, if you see the periodic table, the vertical column, so from your left to right, if you see the 14th column, it starts from carbon. So carbon is the topmost element. It actually belongs to second period. The row that you see, the horizontal row, that's a second in number. First is having only hydrogen and helium. The second is starting from lithium, beryllium, boron, then carbon. So over here, carbon is usually when we go from top to bottom in a group, so its size is going to increase. The element size keep on increasing because the shells keeps on increasing. So carbon is the first element in the you can say in the top in its group. So it's having only two shells, so it's small in size. And small sized atom do always have this probability, or you can say opportunity, to form multiple bonds. And plus carbon is having four valence electrons, it can form four bonds, four covalent bonds, so that opportunity is there with carbon. Then tetracovalency. So tetracovalency means its valency is 4 since it's forming covalent bond. So carbon can form 4 bonds. Now the point over here, C4 plus and C4 minus, why it cannot donate 4 electrons or accept 4 electrons. So there are energy you can say factors. So C4 plus means it need to remove 4 electrons. So when we are removing electrons from an atom, we require energy. So it's a very expensive, energy expensive process for this atom to remove 4 electrons. And if we want to add 4 electrons in the carbon, since it's having only two shells, so there will be a lot of electronic repulsions between already present 4 electrons over here in the second shell of carbon. So that leads to a lot of electronic repulsion. So the C4 minus is not possible. Now this is I'm talking about the complete transfer of electrons. I'm not talking about the polar covalent bond. So carbides C4 minus do exist. So that's only, there is no complete transfer happening over there, but there is a partial 4 minus charge, small charge, which is getting developed over there. So that's a different story. But over here in general, if we say on the basic ground, it is not going to do so. But we do have some exceptions, but it's not going to completely transfer 4 electrons. That is expensive. You can say not expensive, that leads to electronic repulsions over here, but this is expensive process. Then if you go to the third one, catenation. Now catenation is self linking of carbon atoms with other carbon atoms to form long chains or branches or rings. So, what is happening over here is like carbon can form long chains like this. Now, I'm not showing other elements like hydrogens usually we put. So, carbon is always going to form four bonds, right? So, I'm just showing the bonds over here, not the atom. So, this is a straight chain. So, long chains, or it can be a branch. So, branch can be something like this. So again, you have to show the bond because carbon will always form four bonds, four covalent bonds. Then in the form of ring also, closed chain structures, something like this. So that's catenation. Catenation is not only shown by carbon; it can be seen with other elements also. It can be seen in silicon. It can be seen in nitrogen. It can be seen in phosphorus. Many other elements, but carbon is doing a wonderful job when it comes to catenation. Why? Because of its small size, it can form multiple bonds. Now, you can like carbon catenation strength, or you can say ability, is more, or this is more seen compared to silicon. Now, silicon is the second element in the 14 group, carbon silicon. Silicon atomic number is 14. It also is having four valence electrons. So it's a family member of 14 group, carbon and silicon. But silicon is bigger in size. It is having three shells. So because of the bigger size, it cannot form, you can say it can form multiple bonds, but not to the extent that is required for carbon. Then after this, even nitrogen can form catenation, and we can even, after this, we can write for phosphorus. So this is nothing but extent of catenation. That's the order that I've written over here, and so on. So these are the special characteristics that makes carbon very special, and that's why the whole organic chemistry is based on carbon itself. So I'll be stopping over here. We'll be doing the organic compounds, vital force theory, and classification of organic compounds in the next video. So stay tuned, and please, if it was helpful, share with your friends, and like, subscribe, and please comment if you like these kind of videos. If you have any particular topic that you want me to share, I'm going in a particular sequence. At least the basic part is done. Yes, it's going to take a lot of time, but yes, that time for sure will be fruitful. And then I have an Instagram account, that is chemistry569. Like I was not able to find a particular good name, so lazy me. Then so over there, I'm randomly picking up questions and I'm solving in the form of reels. But again, I'm on a social media. It doesn't mean that you have to stay on the social media forever. And most of the kids do this, like they want to learn, and under that blanket, they try to show to their parents that we are studying, but actually they are not. So please try to refrain. Social media, YouTube, Instagram, everything is a secondary way of studying. This is never going to be primary. If it's primary, you are lucky, you are very intelligent, you can actually read from the books, and you can learn, and you can connect the dots. So many other things you can do. But if you are someone who need help, you can connect with me on one to one. You can email me, and we can have an online class. So please try to make this YouTube as a secondary way of studying. The primary is always a book, and the primary is always a single teacher in front of you who is helping you to correct your mistakes wherever you're doing. But this is always going to be secondary. That's why I'm making a shorter video. I want to make a longer video, but that's like too much energy draining, draining from my end, from the student end also. So I don't want to make a long video. So happy studying, keep working hard, do not ever give up, and I'll see you in the next video. Thank you for watching.